Hi everyone. Today we're going to finish our conversations about the Southern Ocean with a module that I actually think is quite fun. We're going to talk a little bit about the biogeochemistry of sea ice in the Antarctic, and I'm going to use this also as a bit of an opportunity to try and sell you on perhaps an honors degree in oceanography, given some of the beautiful photographs included here of the sea ice in the Antarctic. Most of them, or pretty much all of them, taken from our own ship, the S.A. Gullis 2. You should have watched the documentary about that before the VAC. Okay, so the questions we'll answer today are: what does Antarctic sea ice look like? I mean, we hear this term sea ice all the time, but what does that actually mean? This is focused on biogeochemistry, so we're going to talk about the seasonal cycle of nutrients in the ice, and we're also going to look at how nutrients, chlorophyll, and primary productivity in the ice compare to that of the open ocean, and we'll talk a little bit about phytoplankton in sea ice. So this lecture is not going to be particularly deep. It's mostly just to give you an introduction to the idea of sea ice and the fact that there is active biogeochemical cycling in the ice. And you're probably already aware of this, and one of the videos that I want you to watch today goes into this a bit, but the seasonal cycle in sea ice in the Antarctic is the largest seasonal cycle on Earth. And what I mean by that is the change in the sea ice cover from about 19 million square kilometers of sea ice in winter down to 3 million square kilometers of sea ice in summer. That change in that area of sea ice is the largest seasonal cycle on our planet. And you can see on this plot, on this map, the dashed line is showing you the extent of the winter sea ice, roughly. I mean, obviously it changes slightly year to year. And the red is showing you the summer sea ice. So you can see that while most of the sea ice melts back, not all of it does. Notice in particular here in the Weddell Sea, so that's south, that would roughly be fairly close to South Africa. So, but particularly the Weddell Sea, where, you've got the Antarctic circumpolar current going this way, but you've got this gyre circulation in the Weddell Sea like this that ends up taking sea ice and sort of bunching it up in the western part of the Weddell Sea. And the reason that's important is I'm going to show you some photographs of ice from the Weddell Sea. Okay, so so all of us who do research in the Southern Ocean spend quite a lot of time and have access to lots of opportunities to be able to go to sea and sample the region. But what I'm going to show you some photos from is an expedition that we were part of in 2019 called the Weddell Sea Expedition. Some of you may have heard of it because there was quite a lot of press about it, because one of the goals of the expedition was to try and look for the wreck of Ernest Shackleton's ship called the Endurance, but which we didn't find. But it was a wonderful opportunity to do some pretty unique science. So what you're looking at in this picture, I'm sorry it's a bit blurry, is the cruise track of the expedition. So basically over here is the Fimble Ice Shelf, and the Fimble Ice Shelf is the region where South Africa's Antarctic base is located. I'll show you a picture of that soon. And so the expedition went from the Fimble Ice Shelf across the opening of the Weddell Sea to the Antarctic Peninsula. This is the Antarctic Peninsula. And yesterday when I showed you a picture of coastal changes in coastal Antarctica that I said came from the West Antarctic Peninsula, that's from here. But this expedition went down to the eastern part of the Antarctic Peninsula and then down to the Larsen Ice Shelf. And this is Larsen C Ice Shelf, and this was in the news. In 2017, this big iceberg called A68 broke off the Larsen C Ice Shelf, and in previous years there's been massive collapses of Larsen B and Larsen A. These are attributed to warming, although it's not very well understood whether that warming is happening from the atmosphere warming above or seawater warming from below, mostly because it's very, very hard to get here and sample the region, and when I show you the pictures of the ice, you'll see why. But in any case, this big iceberg A68 that collapsed off Larsen C Ice Shelf accounted for about 12% of Larsen C's ice shelf, so it wasn't insignificant. And then, so there was a whole lot of work done in this part of the Weddell Sea, which is very ice-filled, and then came back out and tried to get to the point of where the Endurance was wrecked. And just getting here was an incredible thing that the ship was able to do. Okay, so I'm just going to take the liberty of showing you a few photographs. And most of these were taken by students, and they're all showing some version of sea ice, okay? And I just want you to look at them, enjoy them, and take away the fact that sea ice is not one thing, that it looks, it takes on various different forms, but it is by definition not land-fast ice, okay? So it is ice that is formed by the freezing of seawater, not by the freezing of snow on land, okay? So this is the ice that's responsible for the brine rejection that ultimately leads to deep water formation. So this is also sea ice. It's something called pancake ice, and you can see why. These look like pancakes, and one of these pancakes can be roughly 1 meter or even 2 meters in diameter. Okay, so this is pretty remarkable, and these pancakes kind of all exist in the same place. This would be considered 100% ice cover, even though you can very clearly see seawater underneath. And eventually these pancakes, their edges get all kind of... what's a good word for it, sort of bashed up because they keep knocking into one another, but eventually they will kind of solidify together and form ice flows. Although typically when you reach the marginal ice zone, which is where you start to encounter sea ice, you encounter pancake ice first, and as you go through the pancakes, eventually you get to the point of bigger ice flows and larger pack ice. So here you can see this is also sea ice. It can be absolutely enormous. The flows of sea ice can be so big that, it's easy to stand on them and work on them. I'll show you some photos of that soon. So this is an example of that. This is the ship moored up against an ice flow. This is not an ice shelf or landfast ice. It's just a large ice flow, but it's so thick and so large that people are able to work on it. So what you can see is the ship moored up against it, craning people off onto the ice to work on it. Okay, same thing on the left here. On the right, this is actually a photograph not from the Weddell Sea expedition, but instead from a winter expedition that we did in 2017 going into the marginal ice zone. And in that case, the advantage is that the marginal ice zone is a lot further north, right? Because in the winter, the sea ice comes a lot further north. But the disadvantage, of course, is that you get maybe 3 hours of daylight. So most of the work has to be done in the dark. But here, the reason I want to show you this picture, because I realize it's not very clear, but what you can see is the size of the pancake. Okay, so when we were looking at this photo previously, it was really difficult to get any sense of scale. But when you look at it, like this, it gives you a better idea. And here what you can see are a couple of people trying to deploy some sort of mooring onto the pancake. And this is from that same expedition in the winter. This is actually me, one of my students. And we went out in this, it basically just looks like a window washing basket, to sample on the sea ice. And it was diabolically cold, as I'm sure you can imagine, in the middle of winter. And these immersion suits that we're wearing, you can see we're wearing so many clothes and things underneath them. These immersion suits cost about 50,000 Rand each, and they give you 5 minutes if you fall into the water in the Antarctic. But that just gives you a sense of what happens if you're not wearing one. But in any case, it can get quite exciting out there. Okay, but to go back to the summer, here again, what you're seeing is one of the, they call these rapid response craft or fast response craft that can be launched from the ship and, oftentimes just used to assist with the deployment and recovery of instrumentation, sometimes to take people to and from islands, for instance. I'm not entirely sure what they were actually doing in this picture, but it's a beautiful picture of them up against one of the ice flows. Okay, so then you can see here we're working on the ice flow, drilling ice cores. So again, I like these pictures because they show how large the flow can be. So here you can see that we've drilled this ice core. If you look closely, there's actually this brown layer at the bottom. Well, I'll talk a little bit more about that in a second, but that is a phytoplankton layer or ice algae layer. And here you just get a sense of what that work looks like. So you can see this work is always happening with penguins kind of trotting around in the background. And I mean, they have no reason to fear us, so they just do their thing. And these ice floes can be incredibly thick, at times 5 meters, even more. And what you can see here is as the ice core is recovered, we're drilling into the ice and sticking in a probe to measure the temperature. And, you take samples for all manner of things, salinity, nutrients, pretty much anything that you can think of. This is just cute. The penguins against the backdrop of the ship. Okay, so previously I had said that I was showing you stuff that was done in the Weddell Sea, which is over here. And then I thought I would just show you the South African base, which is called SANAI 4. SANAI stands for the South African National Antarctic Expedition. This base is relatively new. It was rebuilt fairly recently. It's located just here. This region of the Antarctic is considered the East Antarctic, and it's called Droning Maudland. And our closest neighbors are the Germans at the Neumayer base, and this is what the South African base looks like. It's on stilts like this because of the weather, right? Because of the amount of snow and precipitation that happens. And I realize this bottom figure is not very clear, but what it shows you is the actual location of the base. So it's located on top of this rocky outcrop that's called a Nunatak. So to get supplies and things to the base, the ship moors against what is called Fimble Ice Shelf. I showed you on the map previously, Fimble Ice Shelf. And this ice shelf, this is about 30 meters high. And this is like nowhere near the base. There's about 160 miles. The base is about 160 miles, I think, inland. And so the ship has to crane everything off onto the ice shelf, and it has to be carried overland to the base, with some things carried by helicopters. And this is just another beautiful photo of the summertime ice in the Weddell Sea. And when we got into the Weddell Sea, into the Western Weddell Sea, looking for Shackleton's ship, this is what the ice conditions were like. It was remarkable that the ship could move at all. And we did get stuck a couple of times, which is not a trivial thing to have happen. But we have a remarkable vessel, which is really a national asset, and an incredible crew powering it. So, it was quite an experience. And then I just really like this picture showing just the incredible colors of the Agulhas up against. This, again, is just an ice floe. It's not an ice shelf, and you can see, people working on it as the ship is moored. Okay, so hopefully that was a nice little tangent to go off on. But as you can see, sea ice is massive. It's hugely varied, and as you can imagine, I'm sure it's very difficult to sample. So I'm just going to give you a little bit of an overview, okay? But as you know, this is actually an image from the Arctic. It's the best that I could find. And full disclosure, Arctic ice is not the same as Antarctic ice necessarily, but at a very simple level, if we ignore the worms, the processes are relatively similar. So sea ice forms by freezing seawater. Okay, the ice is very porous, which means that it doesn't freeze like an ice cube in your cool drink or in your gin and tonic, right? That's very clear. Instead, it freezes with all of these channels in between the ice crystals. These are called brine channels. And the brine channels are extremely salty because when the ice is forming, it rejects all the salts. So whatever liquid is left in the ice is going to be very salty. And yet somehow phytoplankton, or what we call ice algae, because it is generally thought that they are slightly different from phytoplankton, but these ice algae, they are able to withstand not only these freezing temperatures, but also these incredibly high salinities. But remember that part of the reason that the brine doesn't freeze is its very high salinity, because of course the saltier something is, the lower its freezing point. Okay. So when you see sea ice, you often see that it has this accumulation of algae at the bottom. So it's basically where the ice meets the ocean, because the ice gets all of its nutrients from influx from the ocean. Okay, the ice, as I said, is porous and it's constantly exchanging with the ocean. And so as long as enough light is penetrating through the ice, And ice algae tend to be specifically adapted to flourish under very low light conditions, but as long as there's some light coming through the ice, they are able to grow. All right, so let me show you something about the nutrients in the ice. So of course, the ice looks white and clean and perfect, and it is incredible, but it has also got a whole biogeochemical cycle going on inside it. And so for each of these plots, I'm just going to show you what we know about the nutrients. Okay, in all cases, this is a compilation of data from sea ice cores. So the y-axis is depth in the core, but it's shown as a percentage of depth as a way to kind of normalize, because obviously all the cores will have been different depths. And in all cases, I've indicated the seawater concentration of the particular nutrient, so that we can see how the in-ice concentrations compare. So let's start with nitrate. Okay, the winter concentration of nitrate in the ice looks roughly like the seawater concentration, and that makes sense. In winter, when you're forming all the sea ice, you're going to entrain seawater into it. And I should say that all of these concentrations have been salinity normalized. So that means that, as you're forming ice and rejecting the salts, you're rejecting the nitrate, the phosphate as well. Those are all salts. And so if you took the absolute concentrations, they would be extremely high. But if we normalize for the salinity, so we take into consideration if you were to actually melt the ice, what would the concentration be, right? So it's a mixture of the high concentration that exists in the brine channel and the basically zero concentration that exists in the ice crystals. So in any case, in the winter, you see that the nitrate looks like the seawater concentration, which suggests that it's been entrained from seawater, or, seawater is often breaking over the top of the sea ice. So you can inundate the sea ice that way as well. So then that nitrate gets pretty rapidly drawn down into the spring as phytoplankton or algae in the ice grow. And then by the time you get to the summer, you see that you've actually produced some amount of nitrate, because what happens is that you start to set up a full-on nitrogen cycle inside the ice. So the algae consume nitrate, they generate a large amount of biomass, you start to get bacteria breaking down that biomass, remineralizing it, nitrification starts to happen, and so you end up with producing more nitrate than you're consuming. Okay, for ammonium, we don't actually have much data from the winter time, although to be fair, we actually have new data, but they're not shown here. The seawater concentrations, as you know, are very, very low. Okay, and what we see basically is that ammonium accumulates over the course of the spring and the summer, and this is because as phytoplankton start to produce biomass, and that biomass starts to get remineralized by bacteria, you're starting to accumulate the ammonium. It's not being reused rapidly the same way that it gets reused in seawater. So by the time you get to the summer, you actually have pretty high concentrations of ammonium, and it's this ammonium that is providing the substrate for nitrification that eventually produces the nitrate that we see in summer. Okay, so here I've provided you with a summary of what I've basically just said. Nitrate is reset to the seawater concentration in winter, it's drawn down in spring, and it increases slightly in summer because nitrification outpaces nitrate drawdown. For ammonium, the winter concentrations are unknown. That's not actually entirely true. We now have some data, and they're pretty low. So if I were to put them on this plot, they'd be somewhere like here, which means that you just keep accumulating the ammonium once you have enough biomass to be remineralized. So, it's not that it's not being consumed, it's being consumed at the same time, but it's just that in general, remineralization exceeds ammonium consumption. And as you go over the course of the summer, this is partly going to be driven by the fact that the amount of light is going to decrease, because you're filling the ice up with particles, so the light penetration is more difficult. And by the time you get into sort of like March, April, the incident solar radiation has decreased as well. Okay, so let's look at phosphate. It has a slightly lower concentration in winter than the seawater concentration, and this is because it seems like when phosphate gets entrained into the ice, some of it gets removed by reactions with calcite particles that are in the ice. So it forms calcium phosphates and actually removes it from solution. And then it accumulates over the spring and summer. We're not entirely sure why. It's possible that you get the preferential remineralization of phosphorus over nitrogen, because remember in spring, you see the nitrogen concentration actually go down. Another possibility is that you get phosphate kind of being locked into these metal complexes and so accumulating in the ice. But either way, phosphate appears to accumulate. Silicate seems to have a roughly seawater concentration in winter. In the spring, it's not entirely clear. Possibly it slightly accumulates, and that could be because you're getting the dissolution of silicate particles, and it gets drawn down then in partly in spring and into the summer, because these ice algae are largely diatoms, so they require silicate. Okay, so these two are slightly less straightforward and also slightly more hand wavy, I will grant you that. And so really what you should take away from it is just that there is active biology and lots of different processes ongoing in the ice that cause changes in the concentrations. And that the concentrations are affected not only by what's happening in the ice, but also in the ocean, because of course the ice is exchanging with the ocean, not just when it first forms, but it can keep exchanging with the ocean, over the course of the spring and summer. Okay, so as I keep mentioning, you get ice algae that grow in the sea ice. You often see them in the bottom layer, as I explained with that fairly horrible cartoon earlier on, because this is where they get access to the nutrients that are being supplied from the seawater below. But I mean, they can accumulate to really high concentrations. As we break ice on the ship and the ice is being turned over, you see these extremely dense, dark, greeny brown sort of carpets on the bottom of the ice. That is all the accumulation of ice algae. And so these pictures are basically, or these images are basically all showing the same thing, but here I just show you that the accumulation of ice algae creates food, food source for all sorts of other things, notably krill, which, as you may know, are exceptionally important as part of the Antarctic food web and provide food for many other higher mammals in the Antarctic. Okay, and then I just wanted to show you that this is what sea ice algae or sea ice diatoms, some of them look like, and a lot of them form chains. So when you look inside the brine channels, this is what you tend to see. This is a schematic here of what I mean by brine channels. So it's basically, they're wedged in there, right? If you imagine that this is an ice crystal, this is an ice crystal, and this is an ice crystal, in the tiny space between those crystals, you have this brine channel where this is supposed to be a couple of pennate diatoms, I think. Here's the brine, and then you can see all these bacteria in here. And I think what this image is showing you is that you get the release of all kinds. This stands for exopolymer substances. It's not that important except to say that it's sort of this high organic content, mucousy stuff that's being exuded into the ice channel. And so this is all just part of the food source that then becomes available to bacteria that are then remineralizing the organics to ammonium and the ammonium to nitrate, etc. So again, the point is really just to show you that there's active biogeochemical cycling going on in the ice and to get you thinking about what that means. Clearly, when the ice melts, there are implications for the surface ocean, right? You can also accumulate particles to such an extent that when the ice melts, they just sink because there's such a high concentration of them. And of course, this results in the export of organic carbon and thus the sequestration of CO2. Okay, and then I just wanted to show you this image. This is from a paper the bottom one that recently came out, and I just think it's very cool, where they've deployed these chambers underneath an ice flow, okay, that would require divers going under the ice. And what they're actually doing over here is manipulating the pH to see what happens to the ice algae. So this is all about ocean acidification, but I just thought that it was pretty cool to see how people are thinking about doing this type of sampling. All right, so we've said that you get the accumulation of chlorophyll in sea ice. So what I'm showing here is a compilation of existing measurements of chlorophyll in sea ice, okay? And you can see that those concentrations can get pretty high. The red is as high as 15 milligrams per meter cubed, which I realize might not mean very much, but it will in a second. But even the lower concentrations over here are somewhere between about 2 and 5. But they can get even higher, significantly higher than that. Okay, and this is meaningful when you compare those concentrations to the seawater concentrations. So this is in the most productive season of the southern of phytoplankton growth in the Southern Ocean. And here I'm showing the chlorophyll concentration. The black line is the mixed layer, and you see that it sometimes gets as high as 1 milligram per meter cubed, but often it's much lower, more like 0.5. And so the accumulation of chlorophyll in the ice is to much, much greater concentrations than in seawater. Okay, so what about primary productivity? Obviously, if there are phytoplankton in seawater and they're actively consuming nutrients, they must be fixing CO2. So what you're seeing here is a study that it's basically a model output, but it was based on constrained by data. And what you're seeing are rates of productivity. In early summer, okay, is at the top, and winter it is at the bottom. Okay, so let's start with winter because it's actually easier. And then what the different panels are showing on the left hand side, you're seeing everything in the middle of the sea ice. Okay, so well, maybe it's easier if I first say, and here you're seeing everything in the lower 20 centimeters, right? Less than 0.2 meters. So this is in the ice bottom where the ice meets the ocean, and this is everything above the lower 20 centimeters, okay? And you can see that there's not much happening in the winter, but in the summertime, in that bottom layer, you can see that the rates of primary productivity get really high, up to 0.8 grams of carbon per meter squared, which is the same as 800 milligrams of carbon per meter squared. And so it has been estimated that primary productivity in the sea ice accounts for more than 10% of the productivity that happens in the zone of the Southern Ocean where ice forms, right? Because remember, sea ice doesn't always cover this region. And so there's going to be plenty of open ocean productivity here as well in this part of the Antarctic zone. But of the total amount of productivity that happens in the Antarctic zone, more than 10% of it happens in the ice. But this really only amounts to about 1% of total Southern Ocean productivity. So in terms of total Southern Ocean productivity, it's not that much, even though the absolute rates get very high. But the reason it's not that much is because the absolute rates get very high, but they're only in a very small vertical sort of column of ice, right? If you're getting these rates of productivity in the lower 20 centimeters of the ice, but really nothing else, that's very different from in the surface ocean where the rates might be lower, but you're getting productivity over the upper 100 meters, for example. When you integrate over 100 meters, you get a much larger number than when you integrate over 20 centimeters. Okay, so this is giving you some estimates of the rates of productivity in ice in the Antarctic. Pack ice is the same as sea ice. And you can see that the rates kind of vary anywhere from nothing, 0, to about 50 milligrams of carbon per meter squared per day. And then in the previous, actually, I don't know what on this plot, I think this was for the month. So if it's 800 milligrams of carbon per meter squared for the month, then, the daily rate, this is really going to tax me. The daily rate is on the order of, I suppose, less than 30 milligrams of carbon per meter squared per day. So it's sort of on par with what you're seeing here. And for comparison's sake, in the open Antarctic, in the summertime, the rates are generally a little higher than that. This is now integrated, okay? When you see per meter squared per day, this is integrated. So the rate at a particular depth will be significantly lower, but when you integrate over the whole euphotic zone, which as I just said is 100 meters deep, you get a much higher number. Okay, so this is just to show you the sort of absolute rates of uptake. So what you're looking at here is carbon uptake in the ice, and here you're looking at nitrate and ammonium uptake in the ice. And really all I want you to take away from this is that much like in the open ocean, carbon uptake just means carbon fixation. So carbon is being fixed and nitrate and ammonium are being consumed to support productivity. Okay, and there seems to be a decline with depth in the ice core, which probably has something to do with light, although I've seen other examples where that's not necessarily the case, right? Although in this case it does actually make sense. Okay, and of course, the thing we haven't yet spoken about, but that always matters when we're talking about the Southern Ocean or phytoplankton productivity in general, is iron. And so what you're looking at here are some measurements of the concentrations of iron in sea ice. So the station numbers for our purposes don't matter. But what you should see, so on the left-hand side here, we've got dissolved iron, and on the right-hand side, particulate iron. So particulate iron just means anything that's on a particle greater than about 0.4 microns. Remember when we talked about DOC, I told you about this big debate in the oceanographic world as to what constitutes dissolved and what constitutes a particle. But in any case, you can think of particulate iron as being like iron inside bacteria, for example. If you were to melt an ice core and filter all the particles out of it and measure the iron concentration, this is what it is. Okay, and so the first thing to notice is that the particular concentration is a lot higher than the dissolved concentration, because this is really what's in the particles, and those are the particles that are then going to be broken down, and their iron and their nitrogen, etc., being available for recycling within the sea ice. But you notice here, even for the dissolved iron, that the concentrations are on the order of 5 to 20 nanomolar, which is much, much higher, I just remind you, than the seawater iron concentrations. So, you know, this is as far south as we can get in the south of Africa. This is south of Australia, and here south of Africa, and you see that the concentrations are less than 0.2 nanomolar, and here we're talking about 10 nanomolar. So the iron concentrations in the ice get really high, and this should be consistent with what we understand about the role of ice, right? Remember when we talked about how iron is supplied, we talked about the fact that ice can concentrate iron that's deposited from the atmosphere or that's entrained from the ocean, and then when that ice melts, it acts as a source of iron to surface waters to help stimulate productivity. And indeed, I just wanted to show you sort of a schematic of what that looks like. So what we're looking at here is time, okay, from October through to March. So basically from spring through to late summer. In all cases, we're looking here, I mean, this is just a cartoon. The light blue over here shows you the amount of open water. So the higher the amount of open water, the less ice you have available, okay? The dark blue here is showing you the rate of primary productivity, and the light, very light over here, is showing you nutrient concentrations. So in spring, when we start to see an uptick in productivity, okay, it's largely due to sea ice diatoms. So these are diatoms actually in the ice. The amount of open water we have is very low. These are succeeded, we call it succession, by huge diatom blooms, and now we're talking seawater diatoms that are eventually start to be succeeded by Phaeocystus. We've talked about this previously, because what happens is you run out of iron, so diatoms can no longer be efficient. Okay, and so something like Phaeocystus that is great under recycling conditions takes over. So obviously there's a period of transition here where the bloom is mixed, and then eventually even Phaeocystus isn't going to do very well, and we switch to much, much smaller phytoplankton like nanoflagellates, some kinds of dinoflagellates, although dinoflagellates aren't necessarily small, pico-eukaryotes, for instance, and even some small diatoms. So this is just to give you an idea about kind of bringing some of the ideas that we've talked about together in how we understand this system. Okay, so this is by no means a comprehensive overview of the biogeochemistry of sea ice. I think what you should take away from this is mostly that biogeochemical cycling happens in sea ice, that the ice is an absolutely enormous component of the Antarctic, and so we really need to consider what's going on in the ice if we want to understand the Antarctic's role in, for instance, gas exchange, right? Because if you think about this exchange of CO2 between the ocean and atmosphere, when you now put ice in between, but ice that is porous, so it doesn't represent a total barrier, there's obviously going to be some interesting things that happen. Clearly, phytoplankton are able to photosynthesize within the ice. They consume nutrients. They produce the breakdown of their organic matter produces nutrients. They concentrate iron. When the ice melts, that is applied to the surface ocean. So ice plays a really important role in the biogeochemical functioning of the Southern Ocean. So hopefully I've covered all the questions that I set out to cover at the beginning. I showed you some beautiful photos of what the ice looks like and made the point that it's very variable. We talked about the seasonal cycle of nutrients in the ice, which I did say, admittedly, our knowledge is not perfect. And certainly, while the nitrogen cycling makes quite a lot of sense, silicate and phosphate are a little more nebulous. We looked at how what's going on in the ice compares to the open ocean, noting that even though things tend to be higher in the ice, so higher chlorophyll, higher nutrient concentrations, higher rates of productivity, in an absolute sense, when you integrate, the surface ocean still wins because the euphotic zone is 100 meters deep instead of 20 centimeters. And finally, I talked a little bit about phytoplankton in the ice and showed you some pictures of what they look like.